Hi, my name is Cecil Bozarth, one of the co-authors of the textbook Introduction to Operations and Supply Chain Management. In this short video, we're going to walk through the calculations required to develop a regression forecast with seasonality adjustments. This corresponds with Table 9.9 from the book. So to start out, let's assume we have 2 years worth of monthly data where we have demand information for some product or service of interest. And so if you look at this data, if you look at the demand, it seems to be going up over time, but it doesn't necessarily jump by the same amount each period. In fact, you have some periods where demand might come back before it goes up. So for instance, demand in January 2016 is 51, in February it's 67, falls back to 65 in March, but then it goes up again in April. So if we were to plot this out, in general we would see an upward trend, but we'd also see some bumps that may correspond to some seasonality. So taking this data, I ran a regression model. Basically, I did that by making the period my independent X variable and the demand being my dependent Y variable. And when I ran the regression, I came up with a following forecast model. That the forecasted demand is equal to 98.71 plus 8.22 times the period. So if you look at that, the 8.22 slope coefficient implies that in general, we think demand is going to go up by about 8.22 units per period. So using that forecast model, let's show how we would develop a forecast that fits the past data. So if we are forecasting for January 2016, we would put 1 in for the period. We'd multiply that by 8.22, add that to 98.71, and come up with an unadjusted regression forecast of 106.9. And if we were to do that for the remainder of the 24 periods here, we get some unadjusted regression forecasts that look like this. Now, if you look at those numbers, in some cases they seem to be pretty close, maybe like in April, where the actual demand was 129 and our forecast was 131. But in January, it's way off. Furthermore, in the case of January, we're badly overestimating what the demand is. In contrast, look at June. Actual demand was 272. Our forecast model predicted only 148. So this regression model doesn't really look completely established or useful the way it is. And in fact, we can see that same effect by taking the ratio of the demand over our forecast. So in the case of January, the demand was 51. The unadjusted regression forecast was 106.9. So the ratio is 0.477. Literally, demand was 47.7% of what the actual forecast was. We badly over forecast in that case. Continuing on, we can calculate the demand over forecast ratio for the remainder of the 24 periods we have here. And you see, like we said before, in January we badly over forecast. Our demand was a relatively small percentage of the actual forecast, but in June we badly under forecast. Actual demand was 83.7% above what the forecast was. Or another way to look at it, the demand was 183.7% of the forecast. So looking at this, we realize we may have some seasonality impacts going on, especially since you notice in January and February and March, early in the year, we're badly over forecasting. You get into the summer months like May, June, and July, we're badly under forecasting. And we see that same pattern repeated in 2017. January, February, and March, we over forecasted. May, June, and July of 2017, we under forecasted. So we start getting the feeling that there may be some seasonality here. And in fact, if you actually plotted out the unadjusted regression forecast against the demand numbers, you would see these. So what are we going to do then? Well, we're going to develop some monthly seasonal indices to try to improve the accuracy of our forecast model. So let's start with January. In January 2016, the ratio of the demand over the forecast was 0.477. In January of 2017, a year later, that same ratio was 0.545. If we take the average of those, we get a value of 0.511. So again, the 0.511 is an average of 0.477, and 0.545. So what does this tell us? Well, it tells us for the 2 years we have data, the actual demand turned out to be on average 51.1% of what the forecast was. And that's going to serve as our monthly seasonal index for every January we're going to forecast for. And we complete it for the remainder of the 12 months, February through December. Now, because these are monthly seasonal indices, we'll repeat them as well in the second year. So now we have these monthly seasonal indices set up. The next step then is to simply take our unadjusted regression forecast, which in the case of January is 106.9, multiply it by the seasonal index, which was 0.511, to come up with a new adjusted regression forecast. And what you notice is because the monthly index is less than 1, it pulls the regression forecast down. And in fact, this 54.6 looks much closer to what the actual demand was of 51 than the unadjusted model did. And we see the same pattern being repeated throughout. Let's take a look at June. In June of 2016, actual demand was 272. Our unadjusted regression forecast was 148, but we multiplied that by 1.9, in effect boosted it up to come up with an adjusted regression forecast of 282.1, which is much closer to what the demand actually was than what we had before with the unadjusted model. So, looking then at the forecast errors, the actual difference between the demand and the regression forecast, we can see that these values are much tighter than what we had before. In the case of January 2016, our forecast error is negative 3.6. The biggest forecast error, in fact, we get in terms of magnitude is March of 2017, where the demand was 191 and our adjusted regression forecast was 154. So for all practical purposes, a pretty tight fit. Now, if you think about this, what I have done is I've taken some past data and I've developed a regression forecast model with seasonality adjustments to best fit that past data. So in effect, I've kind of cheated the system to come up with a model by using the data I already had. Would I expect this same forecast model to perform as well in the future? Almost certainly not, because this particular model was tailored to the data I had. But it's at least a reasonable first start. So if I was going to go ahead and forecast for January of 2018, how would I do that? I take 98.71 plus 8.22 times 25, which would be January of 2018. I take that result, multiply by my seasonal index of 0.511 to get my new forecast for January 2018. Now, obviously, as we get more data, we get data for 2018 and 2019, we can rerun the regression analysis. We can recalculate the seasonal indices and potentially come up with a better solution.